Hello, I'm Miles Tails per hour. We will now move on to part 2. Two things we need to tell you. Fourth, the force. For linear, we know mass multiplied by acceleration. Now, we will see the angular force, considered as torque, as a Greek letter tau. As you can see, the mass and acceleration is now transformed to moment of inertia I, and alpha. Also, torque is equal to Rf sin theta, where theta is dependent on angles. To give it a maximum torque, we now say, torque is equal to R cross F. Don't forget to put a cross vector now, and use your right hand to identify the direction of torque. If you have made the torque in counterclockwise direction, the result is coming out of the screen. If the direction is clockwise, then the result of the torque is into the screen. Just like you might have seen screws and nuts, that lets you loosen or tighten them with screwdriver or spanner. Other examples like jars with opening and closing lid, as well as on the plastic bottles and much more. And finally, the momentum. Linearly it was mass multiplied by velocity, and now, for the angular momentum, denoted by L. There are two cases of formulas. L is equal to the moment of inertia multiplied by angular velocity, and also, R cross P. But P is a linear momentum, equal to mass and velocity, the tangential component. Let's take an example. In an ice skating, a girl who tries to spin. By keeping the linear momentum constant, she keeps the hands straight first, its speed is slow. As soon as she folds her arms, its angular velocity will increase. Why does it happen? Because of higher moment of inertia. Other examples you may like to see rotating tops as well. Now, similar to linear formulas, we now transform them into angular formulas. That's why everything looks similar, by the way, from gravitation and straight line. In the next part, we'll solve the numerical questions. Like, comment, and subscribe now on YouTube.